Welcome. Today we are going to start a new topic, that is the binary phase diagrams. In the last few lectures I have discussed about the single component phase diagrams, or what is known as unary phase diagrams. Unary means single component. As a part of that, I discussed the different phase diagrams like water, carbon, iron, sulfur, or even carbon dioxide. And we have probably seen that phase diagrams of single component system consist of two axes, pressure and temperature. So pressure and temperatures are varied, and the different phases for any system are plotted on the diagram. Like, let us consider iron. I know that iron is a very classic system because iron is the bulk component of steels. So iron has basically three different phases at unit 1 atmospheric pressure depending on temperature. The lowest the room temperature phase is alpha phase, which is a BCC structure with a lattice parameter of 2.864 Armstrong. As you hit about 912 degrees Celsius temperature, this low temperature phase, alpha phase, transforms to gamma. And again the gamma phase transforms to another BCC phase with a lattice parameter of 2.94 Armstrong at about 1394 degrees Celsius temperature. So as you know that these phase diagrams basically has two axes, pressure and temperature, because in a pure compound system there is no composition variables. But when you talk about binary phase diagrams, there are three variables present. Other than pressure and temperature, we have another variables known as composition, and these compositions can be represented in many ways that we will discuss very neatly. But let us suppose there are three variables, pressure, temperature and composition in a binary phase diagram. So first we will see how we can actually generate such a kind of phase diagrams and we can use them. So if there are three axes which are mutually perpendicular to each other, pressure, temperature and composition, then the diagram will be a three-dimensional one. Like the one I have shown you here is this picture. You have z axis is basically pressure, and x axis is the composition, and another y axis is the temperature. So as you can see, if we plot for a very simple system like A and B, where A and B are the two components, still the phase diagram is very complex. So first let us discuss that how we can plot the three different composite variables in a system. So I showed you the pressure varies along z axis, composition along x axis, temperature along y axis, and this diagram shows different regions like vapor solid equilibria, solid liquid equilibria, vapor liquid equilibria. This is solid liquid equilibria, this is solid liquid equilibria between solid and liquid, this is vapor liquid and vapor solid. So all these three equilibria are represented in this pressure, temperature, composition, pressure, temperature, composition plot. And if you notice very carefully, we metallurgists are not good at three-dimensional plots like mathematicians or others. So we always like to have two-dimensional plots like two axes. So how to do that? So before I go about it, let me just tell you what is this diagram is about. As I said you, here if you see OA, the point OA is basically corresponding to the univariant point of A. That means this is either melting temperature or vaporization temperature P or A. Similarly, point OB correspond to this point here, correspond to the univariant point of B. It can be anything, melting temperature or vaporization temperature. And the two phase equilibria are exist. Two phase equilibrium means two phases coexist in this lenticular separate regions like vapor plus alpha, V plus alpha, or L plus alpha, or B plus L, where B is the vapor, L is the liquid, alpha is the solid phase. We can represent, and then we can connect them to different curves like here you see a BA to A and then A, it goes above like that. Similarly, for along the B, POB, BB to OB goes up. So that is the way actually we can represent the different phase equilibrium in a 3-dimensional plot. But as you know, such a thing is very cumbersome and complex. So that is why we can use a very clever approach. What is that? We can always assume very simply pressure to be constant. If I assume pressure is constant and pressure is 180 m, 1 atmospheric pressure, then I can take a section along these. I can take a section at 1 atmospheric pressure on this diagram. So how it will look like? Very simple. If I take a section at a pressure is equal to 1 atmospheric pressure, ATM, then it will look like this. Very simple. It will look like this is temperature axis on the vertical and horizontal axis is the composition, and there are two components A and B. So therefore, one composition axis is enough, because if I know one composition, other composition can be easily obtained. Before I discuss what is this inside this diagram, let me first dwell a little bit upon composition. How we can represent composition of two different components in a system? Let us first tell you it. Let us suppose there are two components A and B. Okay, for the simplicity, let us suppose two components are iron and carbon. For a very simple thing, let us assume that. Although this will not follow this diagram, but still. So if I have two components of iron and carbon, and if I know that a binary alloy, basically an alloy means is a mixture of two components together. Suppose binary alloy of iron and carbon consisting of XA mole fraction of XA mole fraction of iron, okay, XA mole fraction is iron, Fe mole fraction, and XB is the this carbon mole fraction. Then I know very simple, this is mole fraction, therefore XA plus XB equal to 1. So if I plot one of these two, either XA or XB, I can get the other one. How? Suppose if I use XB as a plot, as a independent variable, so then I can obtain XA as equal to X1 minus XB. So that is why in a binary phase diagram you have one composition axis, because the other one is easily obtainable by this relationship. Now one can actually use mole fraction, one can use weight percentage, one can use atomic percentage as different units of composition. How we can actually convert one of these to each other? Let us assume that first time is that I take different weights or mass of iron and carbon, suppose in this case. Suppose I take about 80% iron weight percentage and 28% of carbon, okay. So I can actually easily convert this weight percent of iron and weight percent of carbon to atom percentage or mole percentage by using the atomic weights. How we do it? That is kind of easily done. I will show you in the board very easily. Suppose I have a component A with 80 weight percent in alloy and component B 20 weight percent in alloy. So if I know the atomic weight of A, suppose the atomic weight A is AA, atomic weight of B is AB, then I can easily calculate what will be the atomic percentage atomic percentage or percentage atomic, easily calculate of A is equal to, very easily, the weight percent divided by the atomic weight, so 80 divided by the atomic weight of A divided by 80 divided by the atomic weight plus 20 divided by the atomic weight into 100. That is all. It will give you atom percent of A. Similarly, atom percent of B can be easily obtained, is equal to 20 AB divided by 80 by AA plus 20 by AB into 100. That is how we can obtain, but we can convert from weight percent to atom percent. And basically if I know the atom percentage, I can convert this to atom percentage. Suppose this is equal to atom percent of A is equal to A, atom percent of B is equal to BB, then mole fraction of A is equal to AA divided by AA plus BB. Please follow my symbols. Similarly, mole fraction of B is equal to BB divided by AA plus BB. That is how we can convert one to others. So, if I have weight percent of the different components known to me, I can convert this to atom percentage, and from there I can convert into mole fraction very easily. On the other hand, if you know the atom percentage and if you know the atomic weights, you can convert to weight percentage. These are very simple rules or simple mathematical terms. So, in three ways we represent compositions. One is in weight percentage, other one is atom percentage, and third one is the mole fraction or atom fraction, whichever way you define. So, your problems which you will see in your exams can be of data can be represented any of these 3 units. So, you have to convert them from one to other, and basically we can solve a simple problem here which I will tell you. Suppose an alloy, if alloy contains about 80 atom percent of copper and 20 atom percent of zinc, and you have been asked to convert this data to weight percentage. How will you do? And now we know that atomic weight of copper is 63.54 grams, and atomic weight of zinc is about 65.38. They are similar. So, how do I convert from atom percent to weight percentage? Very simple. So, I simply write atom percent of weight percent of, because I have to convert to weight percentage from this. Atom weight percent of copper is equal to 80 into atomic weight of copper, correct, atomic weight of copper is 63.54 divided by 80 into 63.54 plus 20 into 65.38 into 100. Okay. Similarly, weight percent of zinc is very easy to do, is 20 into atomic weight of zinc 65.38 divided by again the same thing, which is denominator we have 80 into 63.54 plus 20 into 65.38. You can solve this problem yourself. I will give the answer the next class. That is very easy. Steps are all done. You can solve your problem yourself. Okay. So, you have understood that composition can be represented in 3 ways: atom percentage, weight percentage, or mole fraction. Phase diagrams can be of different types, like iron carbon phase diagram, carbon is represented in terms of weight percentage, but copper zinc phase diagram you will see this the mole fraction of, or the composition is represented in terms of atom percentage. And there are phase diagram we will see the composition represented as a mole fraction. But the thing which I am trying to stress you upon here is that you must know how to convert one unit to other. If the data are given in weight percentage, you can convert easily to atom percentage by using atomic weights. You have to divide the weight percentage by atomic weight to get the atomic percentage, and from atomic weight atomic percentage you can convert to mole fraction very easily. So, I hope it is clear. Now, let us get back to this diagram, which is a section of this 3-dimensional diagram at 1 atmospheric pressure, and this diagram is shown here in this slide, where you see there are 3 zones one is known as L to correspond to liquid, other one is known as alpha correspond to solid phase, and there is a zone, lenticular or lens separate zone known as alpha plus liquid. The three are three zones. Before I go into this diagram in detail, I like to tell you that binary phase diagrams can be of different types, and we are going to dwell a lot of time on these different types of binary phase diagrams, starting with isomorphous system, then eutectic, peritectic, monotectic and others. But so in all these binary phase diagrams, whether it is a isomorphous system, eutectic system, peritectic system, any other, the axis will remain same. That is what I want to spend time on that. X axis will be always compositional axis represented by either of these three units, and y axis will be always temperature axis. What is going to change is the thing which is inside, thing which is plotted, and this is what you should get into your mind very clearly. Then binary phase diagram is easy to digest, very easy to digest. Once you know that what is there inside and how to read it, then 70% of your job is done as a scientist, as an engineer, as a shop floor engineer, wherever you are working. So that is what we are going to discuss in detail. Now let us consider a system which is known as isomorphous. What is known as isomorphous? I will explain to you. Isomorphous, because the first binary phase diagram which I am going to discuss is known as isomorphous phase diagram. Isomorphous means, iso means same, morphous means same morphology. Obviously this different phase diagrams will depend upon interaction between A and B, two components there. Suppose the two components are such that they are miscible in any proportion, in both in solid and liquid, then the phase diagram which forms is known as isomorphous phase diagram. What is the meaning of miscible in all proportions, both in solid and liquid state? Suppose if I take water and sugar, I add sugar into water, it will get mixed up, but you cannot keep on adding sugar into water and mix it up. Beyond the saturation limit, sugar will not get mixed into water. So therefore that is not completely miscible in system in all proportions. Similarly, if I take a solid, okay, solid obviously has to be metal. Suppose if I take iron, which element if I add into iron will be miscible all throughout? Very difficult answer, very difficult to answer this question. So that means that if I take two elements A and B, and if they are miscible in all proportions, both in solid and liquid, we call isomorphous system. That means if I take 90% iron, 10% of suppose something else, 10% of say manganese, because iron manganese is a very interesting phase diagram. If I take, that will be miscible nicely. If I take 80% manganese, 20% iron, it will be miscible. Similarly, if I take a 50 percentage of iron and 50% of manganese, it will be also miscible in both in solid and liquid. So if they are miscible in all proportions means starting from 1% iron to 100% iron, or vice versa with for the manganese 99% iron to 1% manganese. If in all proportions they are miscible, then we form what is known as isomorphous system. We will later discuss which are the systems which will form isomorphous system later on using homeopathy rules. But let us, for the time's sake, let us assume that we have a system, binary system with two components A, B, which are miscible in all proportions both in solid and liquid state, then only you will have this phase diagram. Phase diagram means we have a region of solid alpha, region of liquid, which are separated by a region of alpha plus liquid. The boundaries between alpha plus liquid with the alpha, there are two boundaries you see here, one is the lower boundary, one is the upper boundary. The boundary here, this one is known as solidus. On the other hand, the upper boundary, or the boundary between liquid and the alpha plus liquid, is known as liquidus. Please remember these words. These are very sacrosanct, you can't change. So the lower boundary is solidus, upper boundary is liquidus. Okay. So that means, what is the meaning of that? Physically it means you have, if you are below the temperature, any temperature below the solidus, you will have only fully solid, no liquid will be present. And if you are sitting anywhere above this liquidus, then you will have only liquid. In between these two only you have solid plus liquid coexist. So this is what is the basically the prime features of isomorphous phase diagrams. And the region of solid plus liquid is looks like a lens. Any lens if you take, it looks like a lens. So therefore we have three regions, solid, liquid and solid plus liquid, and these three regions are bounded by two curves, solidus and liquidus. This is again plotted here nicely, and I am going to discuss little bit more in details, As you see here, again we have liquid, solid, alpha. Why do you use alpha here for solid? You know, in all solid phases, in phase diagrams, I told you earlier also, are represented by Greek letters, and Greek letter starts with alpha. It goes on beta, gamma, delta, many others. So as the number of solid phases will increase, we have to use different symbols, Greek symbols. Only Greek symbols are utilized, no other symbols. This is very well defined. You can't change that. So if you see here again the same phase diagram, temperature versus composition axis plotted, and we have three regions, liquid, alpha and alpha plus liquid. Now so when we have a single phase region alpha, or when you have a single phase region liquid, it is very easy to apply the phase rule. Let us do that first. We know phase rule is given as C minus P plus 2, where AP is the degrees of freedom. So here pressure is constant, we have kept P, the capital P is pressure is 1 atmosphere. So therefore AP will be equal to C minus P plus 1, because two corresponding temperature and pressure is not varying here. So this is the case. Now I will just explain in this class how to apply the phase rule in a single phase region like liquid and alpha. So let us first do that. In a single phase region, here C is the component is 2, because there are two components A and B, and in a single phase region pressure is P is 1, because the number of phases is 1. So AP is equal to C minus P plus 1, that is equal to 2 minus 1 plus 1 is equal to 2. So that means degrees of freedom is equal to 2. What is the meaning of that? Okay. Let us select a temperature in a single phase region, T1, right. Now I can have many compositions, you can draw this composition vertices, many such that where alpha is stable. Similarly, if I take a different temperature T2, alpha is also stable at many compositions. So that means I can vary both temperature and the composition simultaneously, still alpha will be remaining alpha, stable, no change. Similarly, if I take a liquid, if I consider temperature T3 here, okay, forget about this T1, TA, T3 here, and I can have different compositions where liquid is stable. If I change the temperature, even all liquid is stable at different compositions. So that means I can vary both temperature and composition simultaneously, still I will not change the liquid phase will remain stable. This is the meaning of F equal to 2. That means I have 2 degrees of freedom, I have 2 handles, I can change them simultaneously, but I will not change the phase. Phase will remain either liquid or alpha, whatever way, whichever single phase region you are in. I hope this is very clear, because this is what is very important things to apply phase rule. This is the way you have to apply. In the books also they will describe you very nicely, so please read the books. Now in the next class I will discuss how to apply it in the 2 phase region alpha plus liquid, and how to use other diagrams, other things to discuss about that.